Now, I am discussing about application of nanomaterials in structural engineering. Structural engineering is a sub-discipline of civil engineering in which structural engineers are trained to design the bones and joints that create the form and shape of human-made structures. Structural engineers also must understand and calculate the stability, strength, rigidity, and earthquake susceptibility of built structures for buildings and non-building structures. Nanostructured materials have several advantages, including lower elastic moduli compared to large grain materials and very high hardness and strength. For example, nanocrystalline materials with 10 nanometer grain size are 2 to 10 times harder than the large grain size 1 millimeter materials. These nanocrystalline materials show increased ductility and sometimes even so superplastic behavior. Improved mechanical and thermal properties of nanostructured materials have been made them attractive for structural applications. These nanomaterials, such as metallic, ceramic polymers, and composite materials, could potentially enable development of materials with significantly higher strength, plasticity, and ductility. Either as a bulk structure materials or as a thin film coatings, nanostructured materials could provide unique properties for their structural applications. Thin film coatings of nanomaterials could enhance surface properties such as corrosion resistance, friction, and wear resistance without affecting the bulk properties of the materials. For example, typically nitriding and carbonitriding of steel surface significantly increases its hardness and wear resistance. In structural engineering, there are carbon-based metal-based nanomaterials, semiconductors, dendrites, neuron clips input from other cells, nanocomposite, and nanohybrids that can improve the construction materials and bring them completely new capabilities. Nanotechnology is revolutionizing structural engineering by enabling the development of advanced materials with superior properties and new capabilities. Carbon-based nanomaterials, example, carbon nanotubes, graphene, fluorine. Application and structural engineering enhance mechanical properties, exceptional tensile strength, elasticity, and stiffness, improve the durability and load-bearing capacity of materials. Self-sensing concrete incorporation of carbon nanotubes allows concrete to monitor stress, strain, and damage autonomously. Lightweight structures, high strain to weight ratio enables the development of lightweight and efficient structures. Metal-based nanomaterials, example, nanoaluminium, nanocopper, nanosilver. Applications, corrosion resistance, protects steel reinforcement in the concrete against environmental degradation. Thermal conductivity, enhance heat dissipation in the building materials critical for thermal management. Antimicrobial surface prevents microbial growth in water pipes and construction materials. Semiconductors, example, nanostructures of silicon, titanium dioxide, zinc oxide. Application, photocatalytic self-cleaning materials, titanium coated, titanium oxide coated surface, decompose organic pollutants using sunlight. Energy efficiency integration with solar panels for enhanced energy capture and storage in buildings. Dendrites biological inspiration mimicking the dendritic structures of neurons can improve the connectivity and distribution of materials at the molecular level, increasing strength and flexibility. Such structures can influence the creation of self-repairing materials by mimicking natural healing process. Nanocomposites materials reinforce with nanoparticles to achieve superior characteristics. Example, polymer nanocomposites enhance elasticity and resistance to wear and tear. Cement-based nanocomposites incorporation of nanosilica or nanoclay improves hydration process and mechanical properties. Nanohybrids materials combining organic and inorganic nanostructures. Application enhance durability. Hybrid materials can provide both flexibility and toughness. Improved multifunctionality incorporates properties like thermal insulation, sound absorption, electromagnetic shielding. Future capabilities in structural engineering, self-healing structures, materials capable of detecting and repairing microcracks autonomously, energy efficient buildings, integration of nanosensors for smart monitoring and energy optimization, green construction, use of nanomaterials to reduce carbon dioxide emission and enhance sustainability. Okay, it's all about application of nanomaterials in structural engineering. Thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience. That is now. Bye bye. See you again.